So I think we should start. It's just gone past 8 a.m. So my name's Andrew Zalesky. I'm from the University of Melbourne in Australia, and I'll be chairing this morning's session on dynamics of functional connectivity. My co-chair is Raphael Lejoie. I'd like to begin by thanking our speakers, Diego Vidaura and Raphael Lejoie, as well as Joanna Cabral, for participating in this morning's symposium. I'm going to kick off the session with a brief introduction to dynamics of fMRI and present some of the work that we've done in this area over the last 2 years. And then I'll hand over to the other speakers to present on some more detailed topics. So to begin with, I just want to give a very brief overview of what is dynamic FC. And at the most basic level, dynamic FC can be mapped using sliding window correlation. So what we can do is extract our bold signal from a pair of regions of interest and slide our window across time. And for each given window position, we can compute our measure of functional connectivity, whether that be Pearson correlation or some more advanced measure of connectivity, just using the data that's encapsulated by the window. And so then we can slide the window along, and as I've shown there, we can map a time-resolved measure of functional connectivity, in other words, dynamic FC. Of course, we can repeat this then for all possible pairs of nodes, and as I've shown at the bottom of the slide there, this gives rise to a series of connectivity matrices. So this gives us a snapshot of the network at each particular time point, at each particular sliding window. So this is the most basic measure of functional connectivity. However, over the last couple of years, there's been more advanced methods that have been developed. I've listed a few there, and our speakers will discuss those in a little more detail. One of the main limitations of the sliding window, well, there's actually many limitations, but one of the key limitations is the arbitrariness in the choice of the window length. So if we choose a window that's too long, we can potentially overlook dynamics that are occurring at a fast scale. In contrast, if we choose a window that's too short, we can potentially map spurious fluctuations that are due to the finiteness of the sample, due to too few sampling points. So a couple of years ago, Nora Leonardi and Dimitri Vanderville proposed a simple sinusoidal model to help guide the choice of window length. They considered two sinusoids of frequency f, and these sinusoids were in perfect phase. And they devised an analytical expression for the covariance between those two sinusoids. So covariance here was the measure of functional connectivity. And in the plot that I'm showing on the bottom there, each line corresponds to a distinct window position, a distinct point in time. And so what we can see is that for very short window lengths, so for example 20 seconds, we have covariance that varies between, say, 0.2 up to about 1.1. When we know the ground truth here is the covariance is 1. So we have two sinusoids that are in perfect sync with each other, and therefore there's no dynamics. The ground truth is a covariance of 1. As we increase the window, we see that once we get to a window length of 40 seconds, the curves converge. So irrespective of our window position, irrespective of where we are on time, we get to the correct value. We get the ground truth, which is a covariance of 1. And they use this fact to guide the choice of window length. So this crossing point, where all these points converge to each other, that's the point just there, this is the reciprocal of the frequency, so the reciprocal of the frequency of the sinusoids. And so they proposed, Vanderville proposed this as a rule of thumb, so the window length should be chosen to be greater than the reciprocal of the minimum frequency. Now with fMRI, the slowest frequency that we're typically interested in is around 0.01 hertz, and therefore this suggests that the window length should be 100 seconds. More recently, in some work that I did with Michael Breakspear, we looked at this model in a little more detail. So not only did we consider the null case, where there was no dynamics in the sinusoid between the two signals, we also considered a case where we actually we introduced dynamics, and you can see that here we modulated the sinusoid by a slow frequency of a frequency of denoted f0 here. And we can see that at given times, the two signals are anti-correlated, then they become correlated and anti-correlated again. And this is what we define as dynamic FC, this behavior of going in and out of correlation. And this led, I won't get into the mechanics of this, but this led to a framework, a statistical framework to test for dynamics in a signal. So basically the colored curves, the red and the green and the blue, provide us with confidence intervals for the null hypothesis of an absence of dynamics. And this is derived from the null case, from the first two signals that I've shown there. The black curves, each of the black curves corresponds to a different position of the sliding window. And the way the test works is we say that we reject the null whenever we see that one of the black curves, so for one window position, exceeds, so it's either greater than or is below the colored confidence interval. And so what we found here is that we could reject the null for window lengths that were substantially shorter than the 1 on F rule of thumb. So we can see here that the black curve exceeds this confidence interval for windows as short as, say, 50 seconds. So despite this, sliding window correlation still has other limitations as well. I won't go through those here. So in more recent work, Mengor-Peterson has devised a method called IPSA. This is some work that we did earlier this year. It was just published, actually, where this particular approach doesn't require the choice of a window length. So what we do here, we once again extract a signal, the two signals for a pair of regions. It's very important in this case that we bandpass the two signals. And then using an approach or computing the analytic continuation of the signal using the Hilbert transform, we can derive the instantaneous phase and the amplitude of those two signals and then estimate functional connectivity as the difference in phase. And so what Mengor did here, he compared his IPSA approach with sliding window correlation. So basically IPSA doesn't mandate a choice of a window. So we have one estimate of dynamic FC with IPSA. With sliding window correlation, we have a different estimate for each window length. And so he's compared window length with each window length with IPSA. And what came out here is we see that the strongest correlation between IPSA and sliding window correlation is a window length of around about 30 seconds. That's where we see the peak here. The two curves here correspond to two bandpass, the range of the bandpass filter. So you may ask, once we've mapped our connectivity matrices as a function of time, what can we do next? How can we use this information to understand brain network organization, the dynamics of brain network organization? So one approach is to use graph theory. We can use network measures to characterize behavior as a function of time. So this is one very simple measure. It's referred to as nodal efficiency. This can be computed on a per node basis, and it essentially tells us how well a particular node is integrated with the other nodes in its network. In essence, this is the shortest path from the node of interest to all other nodes. And so we can compute this for every node in our network and do this for every time window. So in other words, for every time point in our time resolved measure. And therefore we can plot a dynamic curve of nodal efficiency. So we see here for node 1 that this shows rather rapid fluctuations, whereas node 2 is rather stable as a function of time. So we did this is work with Michael Breakspear now a couple of years ago. We did this in data from the Human Connectome project. So this heat map that I'm showing you here is nodal efficiency as a function of time for each node. So we see that the vertical axis here are the nodes in the network. The horizontal axis is time. And the interesting thing that we noticed here, we see that there is multiple nodes that synchronously transition to a high efficiency state. So we can see here where I've indicated with the vertical box that multiple of our nodes enter that state where efficiency is increased. They stay in this state for some time and then they go back to a low efficiency state. So we used a vector autoregressive model as a null, and we didn't find this behavior in the VAR. I should point out though that Raphael, one of our speakers, has recently published some work on a more sophisticated null, a multivariate vector autoregressive, and shows that it's much more harder to reject the null with this more sophisticated null model. I won't go into the details of that here. You might also ask that, is this behavior just due to head motion? Perhaps the person moved in the scanner, or perhaps the fact that we have this synchronous behavior across nodes is trivially owing to, say, a physiological confound. And to exclude that possibility, we ran a neural mass model simulation. We had neural masses that were interconnected according to the connectivity matrix of the macaque, and we replicated that same behavior. And we can be sure that in the macaque, there is no notion, no concept of head motion or physiological noise. This is purely a neural a simulation of interconnected neural masses. Sorry, I gone too fast. My apologies. So the video that's should be playing here. So it's okay, there you go. So that's the video there. What I'm showing here is nodal efficiency now as a function of time rendered onto the cortical surface. And what we then ask, what are the practical consequences of these dynamics? What can we learn from these dynamics? So in some recent work with Luca Cocchi, what we did, we put a person in a scanner and we presented them with a pseudo-random sequence of two stimuli, faces or dots. And we trained an MVPA to decode whether the person at a given time point was presented with the facial or the facial stimuli or the dots. And we were able to decode this with an accuracy of around 70% using fMRI activation and MVPA. What we then asked, we thought that these high efficiency states might represent a period of time when the brain is in a responsive or a vigilant state. And so what we did, we separated the stimuli according to whether they were presented in a high or low efficiency state. And we hypothesized that those periods where the stimuli were presented in a high efficiency state would lead to improved decoding performance. This is because the brain in that particular time epoch would be vigilant, it would be more responsive. And indeed, that is what we found. So what I'm showing here is decoding accuracy for the MVPA, segregated according to the high efficiency and low efficiency states. So in high efficiency, decoding performance is around 5 to 10% increased relative to the low efficiency states. So this provides a functional consequence of these fluctuations in network efficiency. So another project, this is work that was just published by Akil that we did earlier this year. Most of functional connectivity dynamics is focused on dynamics in time, temporal dynamics. What we're interested in doing here is investigating dynamics in space, spatial dynamics. So we allow networks, canonical resting state networks, to grow and shrink as a function of time, as I've shown here for the default mode network. We characterize those spatial dynamics based on the volume of the network, so the number of voxels that comprise the network at each time point. So for each sliding window position, we characterize the volume. And Akil did this for 14 canonical resting state networks. And what we wanted to do, we wanted to determine whether this particular behavior, that is dynamics in space, would be able to differentiate diagnostic status in patients with schizophrenia. So we trained an SVM to differentiate between patients and controls using this particular spatial characteristic. In fact, we trained 4 SVMs. The first one was the classic static functional connectivity. We then had dynamics in time, so our only feature was characterizing fMRI dynamics in time. And then the classifiers there that I've called class 2 and class 4 represent this novel characterization where we're looking at dynamics in space. And so what we see there, as I've shown for the 3 plots, accuracy, sensitivity, and specificity, is that we can improve the classification, the prediction of diagnostic status by taking into account spatial dynamics. So you can see there for class 4, we can predict diagnostic status with an accuracy approaching 90%. However, if we use the classic interpretations of dynamics, so that's dynamics in time, our accuracy drops to just below 80%. So this is telling us that these dynamics that we see in space add value, provide additional discriminatory power relative to the classic conceptualization of dynamics in time. So we know now that this has been around for a while, that functional connectivity and structural connectivity are related. And in some work that I did with Fernando Calamanti last year, we tried to understand the relationship between function and structure dynamically. And so the image that the video that I'm showing here corresponds to, each frame here corresponds to a 60-second time window. And the areas of the warm and the dark colors correspond to white matter. So when a white matter area is colored in a warm color, this corresponds to a particular time point where that fiber bundle is supporting or facilitating a functional connection. So we can see that there's a rich repertoire of dynamics here as a function of time. I won't go into the mechanics of this approach, but essentially what we're doing, we're projecting functional connectivity onto the streamlines derived from tractography. We've used this approach to parcellate the corpus callosum as well. I won't go into the details of that here. So finally, I just wanted to flag some very recent preliminary work by Amir Amidvania and Mangor Peterson. The hypothesis here is that we expect that regions that show the greatest dynamics, so we see variation in dynamics across the cortex. Some regions are more dynamic than others. And our hypothesis here was the greatest metabolic consumption would be in regions that show the most rapid dynamics. And so we acquired simultaneous PET and fMRI in this experiment. And what Amir has done here is he's mapped spatial maps on the right of fMRI dynamics, and the maps on the left correspond to PET. And he's then correlated a spatial correlation to determine if there's any relationship, a regional relationship between these two measures these two dynamic measures. And indeed there is. So as I've shown on the bottom, there's a correlation of 0.4 between the two if you look at the mean. Take a look at Amir's poster if you're interested in further details. So I'm going to stop there just to note that my slides are available for download on this website. So please feel free to download them. I've listed a few posters there of the work that I've described. The Keels poster on the spatial functional connectivity dynamics. Mangor has a poster, I haven't discussed that here, on multi-layer fMRI networks. Keo Seguin on navigation. That's a project I haven't discussed here. The PET and fMRI dynamics is a poster by Amir Amidvania. And finally, there's some work using fMRI to biotype ADHD patients. And just to conclude, we're currently looking for a research fellow in networks neuroscience at the University of Melbourne. It's a 3-year position. Happy to talk to anyone that's interested after the talk, or check out the website for further details. So I'm going to stop there. Perhaps we may have time for one question. Otherwise, we'll move on to the next speaker. Thank you.